Swayam Prabha. Digital India. Educated India.
So, let's go over with the isolated DC-DC converters. We had come until push-pull. In push-pull, the way the duty ratio is defined in Daniel Hart is a little different from what I had defined. I had defined basically whatever is the on time divided by T by 2 as the duty ratio. This is what I had defined, right? This was my definition. Whereas Daniel Hart actually is defining this as T on divided by T, the entire T. And T on of every switch. There are two switches, you remember? So if you actually look at the push-pull configuration, I am going to have essentially two transformer windings like this, and one is connected through a switch here. This is connected in the middle, and the other one is connected through the second switch. This is how they are connected, right? Okay? And we said that if we are defining the dot here, this has to be the dot, because I'm assuming that they are connected in series, not in anti-series. They will add up together in terms of voltage. On the other side, I'm going to have again two secondary windings. So if I may call this as N1, this is also N1, whereas this is N2, this is also N2. The number of turns are N2. So I am going to have here a diode, one more diode here, center tap rectifier configuration, and then I'm going to have from here an inductance. A freewheeling diode is not necessary because these two diodes will be able to take the function of the freewheeling diode. I don't have to put any explicit freewheeling diode, and after which I'm going to have a capacitor and a resistance. Right? So this is the load and this is my LS. That's what we took as the inductance, which is similar to the inductance in a buck converter. That's what we took. Now, if I am turning this on, I am going to get a positive here and negative here. That is when let us say this is some S1 and this is S2. These are the two switches. When S1 is on, I am going to have positive here and negative here. So correspondingly, I will have positive here and negative here. That's why we said that whatever is the voltage across this switch will be twice whatever is the voltage across one half of the primary, right? So at this point, if I want one of the diodes to conduct, let us say this is D1 and this is D2. If when N1 is on, if I want D1 to conduct, I should have probably the dot along this, right? Hopefully. So if I have the dot along this and I have the other dot along this, so I will have positive here, negative here, again positive here, negative here. So D2 will be reverse biased and D1 will be forward biased, right? So D1 is forward biased, and whatever is the voltage that is coming across this secondary will be N2 divided by N1 multiplied by whatever is my input voltage. If I say this is Vin, N2 by N1 multiplied by Vin is the voltage that is coming across one half of the secondary, which is conducting right now, right? So I will have D1 conducting during when I'm going to have S1 on, right? This is going to be the voltage, and I have V0 here, and that V0 is fairly a constant because the capacitance value is fairly large. The ripple is minimum. So we can say this minus V0 multiplied by whatever is the time duration for which this was on. So I should multiply this by D times T. Actually, I had multiplied this by D times T by 2 because I had defined the duty ratio that way. That's all is the difference. Okay. So what Daniel Hart shows is something like this. D times T is equal to, right, whatever is the change in current in Ls, which is delta I Ls. Right? This is during the on interval. And when I turn it off, it is exactly similar to what we had in the case of the buck converter when we had turned off the switch. Right? So when both of them are not conducting, that is off interval, when S1 and S2 both are off. Right? Under this condition, what he has written is half minus D multiplied by T, because this is repeating itself for every T by 2. S1 is on for a very short while in T by 2. Then we are going to turn both of them off. Okay. Then T by 2 you have reached, when the entire circuit has reached the point of T by 2 time, then you are going to turn on S2. Then T by 2 plus whatever is the time duration of T on, for that duration second switch is going to be on. So we are essentially looking at something like this. The waveform will be somewhat like this. If this is my T, I am going to have, for initially this is, let us say, T by 2 and this is T. So I am going to have one of the switches on for some time. Then the next switch is going to be on for some time. So this duration we are calling as dt. This duration also we are calling as dt. This is on corresponding to S1 and this is the pulse corresponding to S2. One minus D multiplied by T by 2 we should have done, provided we assume that whatever I had done, T on by T by 2 is the duty ratio. If I assume, then that is right. But as per Daniel Hart, he has essentially assumed T on by T. That itself is equal to D. So he is not taking T by 2 here. He is taking T. That's the reason why we are looking at this little differently. That's why when I derived the other day, we didn't get the 2 factor. Whereas this fellow gets a 2 factor. Daniel Hart gets a 2 factor. There is nothing wrong if you get a 2 factor or you don't get a 2 factor, as long as you define your duty ratio properly. As simple as that. That's all. Right? As long as you define your duty ratio properly, you understand what is duty ratio, then it's perfectly fine. There is nothing wrong. Right? So this is essentially the off interval. So I'm going to get again Ls multiplied by delta ILs in steady state, where this is decreasing current, whereas this is increasing current. This is going to be increasing current. Right? Now you have to just equate these two, from which you should be able to get whatever is your expression for V in by V naught. So we can say V naught multiplied by half minus D multiplied by T equal to N2 by N1 multiplied by V in minus V naught dt. 1 minus, yeah. So this will be essentially, when you add the two, you should be able to get finally whatever is your, this 2 factor will also come into picture. So we will have 2 multiplied by N2 by N1 into V in multiplied by D. That's what we will get as the overall expression for your output voltage. Right? So V naught is going to be, I think, N2 by N1 multiplied by V in multiplied by D multiplied by 2 also, because of the way we have defined the duty ratio. Right? So the same thing holds good very clearly for S1, and one more thing you have to remember is this particular switch is also going to face twice the voltage as the reverse biasing voltage. Whatever is the output voltage, if I may say, that is V in multiplied by N1 by N2, each of the diodes will also phase twice that voltage. Vin multiplied by N2 by N1, if it is, that is the voltage that is coming up as the output. That multiplied by 2 will be phased by each of the diode which is not conducting at that instant. Because the secondary voltage is induced on the other side also. It will not conduct, alright, but the voltage is very much induced. It is open circuit voltage, which will come up across any diode which is not conducting. So the diodes have to be rated for much higher voltage. Same is the case with the devices. These also have to be rated for much higher voltage than whatever actually they are delivering. Right? They are delivering much less. So this kind of one diode conduction, this is what we talked about earlier. In power supplies, what we worry about is the drop. So if the output is only 5 volts, you don't want to have 1.4 volts as the drop. That's the reason why we don't use bridge rectifier. If you use a bridge rectifier, 2 diodes will come into picture in terms of the conduction path, and you want to avoid it. That's the reason why we normally use this, although the voltage rating becomes much higher. And if it is a 15 volts circuit, you have to rate it for 30 volts and a factor of safety, right? That is not much really, because the voltage rating actually, unless you go beyond kilovolts, the cost does not increase tremendously. Only when you go beyond kilovolts level, the cost increases tremendously. The currents or the overall power rating increases the cost quite a bit. And more than anything in power supply, we are worried about regulating the output voltage. So we don't want to have too much of drop, and too much of drop means there will be definitely a lot of copper losses across the devices. That means you have to put bigger heat sinks, and then the size will increase further and further. So you don't want to increase the size quite a bit. Okay, so much so for the push-pull converter. Right? The last 2 converters in isolated topology are half bridge and full bridge. So let us look at half bridge converter. We will revisit this half bridge topology again when we come to inverters. We will be looking at this, extensively. But right now, let us look at this especially as one part of the DC-DC converter. So half bridge is a general circuit which can be used for DC to AC conversion as well. So this is my input voltage, and I'm going to have 2 capacitors connected which will divide the voltage equally, because we will choose in such a way that the values are the same and they are connected in series, which means half the voltage will come across each of them. Now we'll have one switch here and one more switch here, right? And let me call this as S1 and this as S2. They are complementary. We will not have S1 and S2 on simultaneously, because if I try to turn on both of them simultaneously, there will be a dead short circuit across the capacitor. That condition is generally known as shoot through. Shoot through is deadly for any of the inverter circuits or any kind of bridge circuit, because you are going to essentially short circuit the entire capacitor path. The currents will be enormously high across the switches as well as across the capacitance. So it is not good. So shoot through we have to avoid. So S1 and S2 cannot be on simultaneously. So even if we assume that S1 is going to conduct for 50% of the duration and S2 is going to conduct for 50% of the duration, we have to necessarily give a small delay between S1 and S2, which we call as dead band. Normally we call that as a dead band. In the inverter, very often we may have a complete square wave output. S1 when it conducts, maybe we'll get a positive voltage. When S2 conducts, it will be a negative voltage. But between S1 and S2, we necessarily need to give a small delay. S1 has to turn off completely before S2 takes over, like what we talked about in the case of cycloconverter. Same thing. So we have to make sure that P converter is turned off before N converter gets the firing signal. It's the same thing. So here S1 and S2 have to be completely mutually exclusive. Now from here I'm going to take the output to the primary of a transformer like this. So if I say this is plus, this is minus, very clearly this is plus, this is minus, this is plus, this is minus. This is how it is going to be. And let me call this as C1, this as C2. If I turn S1 on, I'm going to have, let me say this has N1 turns, right? It is essentially going to, the current is going to flow through the capacitor, through S1 into this winding, and then it is going to return to the same capacitor. This is how it is going to be. This is the path as far as the current is concerned. Please note, under this condition, capacitance 1 is discharging, capacitor 2 is idling. So sometimes what we face as the problem is that C1 gets discharged quite a bit, even within a few microseconds or a few milliseconds, and C2 actually gets overcharged because the voltage is V in across C1 and C2 put together. So sometimes we face the problem of a voltage imbalance between C1 and C2. But if we choose sufficiently a large switching frequency, then we would not be seeing this much, because the time constant involved will be quite large, because the capacitance values are normally large, because of which the imbalance will not be visualized so much normally. Okay, but this is normally a prevalent problem, especially in inverter, when I use this as an inverter circuit. So when S1 is on, I am going to get again, let us say this is S1 signal and this is probably T by 2 and this is going to be T. So this is corresponding to S1's firing signal. So if I try to draw what is the firing signal for S2, I'm going to again have S2 conducting from here for the same dt duration. So if I call this as dt, this will also be dt. So this particular signal corresponds to the firing pulse of S2. Okay. Now what is available on this side will be whatever is the voltage that is coming up, that is V in by 2. So what I get as the voltage whenever any of the switches will be on will be V in by 2, neglecting the imbalance between the two capacitor voltages. Because this is going to be my load. I am going to show the load on this side. I have the secondary here like this. So let us say this is N2, this is also N2. And I'm going to have diode, here also a diode. Same thing, like what we got as a center tap rectifier. So I'm going to have the load here, which means again an inductance, capacitance and a resistance. So this is my Ls and this is R. Right? Same as what we got earlier. So if I say that, for example, the dot for this is here, I can show the dot here, then dot here. So if I say that S1 is on, I am getting positive here during this portion. So obviously this will be positive. So this will conduct. D1 will conduct. And when I turn off S1 and turn on S2, at that point I am again going to get the voltage in the opposite sense. Look at the conduction path. So I am going to have from plus, it is going to go like this in this direction, and then it is going to go like this and return through S2. So the current is flowing in the opposite sense in the winding. So you create positive half and negative half across this winding, which is the high frequency transformer primary winding, as and when you turn on S1 and S2 respectively. Right? So this is all square wave, clearly. Whatever we are getting is a square wave, because we are giving V in, which is a constant value. So DC-DC converter, ye sab chalega. There is no problem. But when we are looking at inverter, we have to look at modulating this wave in such a way that we get a sinusoid. How do we get a sinusoid? That is a major chunk of, the control of the inverter, right? Which we'll be looking at eventually. So we are essentially looking at these as the voltage. So if I look at what is the voltage here, it will be N2 divided by N1 multiplied by V in divided by 2. That is what is coming up as the voltage when any of the switches is on, right? So this minus whatever is my V0 again multiplied by dt equal to Ls delta ILs. This is when S1 or S2 is on, any one of them is on. Along with that, of course, either D1 or D2 will be on. Either D2 or D1 will be on. So similarly in off condition and S2 both are off. Right? We are going to get V0 multiplied by, we have to write it the same way, half minus D multiplied by T. Right? I am using exactly the notation of Daniel Hart. Right? That is going to be Ls multiplied by delta ILs. So here this is increasing current. This current is increasing, whereas this is decreasing. Right? So there will not be the 2 factor, because this 2 factor will get cancelled with the 2 factor what we are getting here in the other one. So I think you will get something like V in multiplied by N2 by N1 multiplied by D. This is what you should be getting as the output voltage in this particular case, which is half bridge. And when we use half bridge, generally in many of the computer power supplies, what we use is half bridge. PC, personal computer SMPS, what we use is half bridge. Generally, we will have one single primary and either multiple secondaries, or if we are talking about 3.3 volts, then 5 volts and 12 volts. So we may have one single secondary with multiple number of turns with taps. So I can get maybe 3.3 volts from here, plus 5 volts from here, plus 12 volts from here. If I need plus 15 or something, I can have more number of turns, but I can ground this portion. This can be grounded. This ground is different from the primary side ground. The primary side ground is connected to the high voltage power supply. In all probability, I may have a 230 volts, I will have a diode rectifier, a capacitor filter which is giving me V in. Right? And after that, I am stepping down everything using a high frequency transformer. So this side ground, whatever I have, is different from the other side ground. That this side is power ground, whereas this side is going to be electronics ground, which is low voltage and low current compared to what I will have on this side. This will be high voltage. Right? And if I want negative voltage, then I might have to just make it the opposite way. I will ground the positive terminal and the negative side will be actually available as the negative voltage form. That's it. So this is the way normally you are going to have the half bridge converter working, especially in PC power supplies. So they want to utilize the core to the maximum extent just by using the same thing. So this might carry higher current because this has to supply whatever is 3.3 and 5 also. So this is common to both. So it will carry really a large current. So when we design the transformer winding, we have to be really careful in terms of the rating what we are choosing for the current carrying capacity. The last one in isolated DC-DC converter is full bridge. And full bridge is used in many applications where we require very high power, like 10 kilowatt, 15 kilowatt rating. So it starts almost from 100, 200 watts. It extends until easily 15 kilowatts, 10, 15 kilowatts. So it is having a very versatile range in terms of its application. So in full bridge, I'm going to have this as my DC power supply, which is V in, and the connection is very similar to what we saw as the full bridge rectifier. So I'm going to have two switches connected in one leg of the bridge, and there are two legs basically, right? So if you may recall, we used to draw this as the full bridge converter, right? These are the two diodes and these are the two diodes, and we used to connect the DC here. It is exactly the same way. DC load is connected here and AC is here. Similarly, we are going to tap our AC from here. The AC is tapped from here. Okay? And then we are going to have the primary of the transformer connected here. Right? Let me call this as S1, S4, like what we had numbered earlier. This is S2, S3. Okay? Or S3, S2, either way is fine. So we should say S1 and S2 are complementary, S3 and S4 are complementary. They will not conduct at the same time. They are mutually exclusive, right? Because if I try to give firing pulses to both of them, again there will be a shoot through. So I have to be careful not to give the firing pulses to S1 and S2 together and S3 and S4 together. So if I am having S1 and S4 conducting, I am going to have the current flowing like this, flowing from here, flowing through this, like this, and then it will come down through S4 and return to the negative. This is the way it is going to conduct, right? This is the path that I am going to have. What did I draw? This is this way, right? So this is going to go from down to up, right? So maybe this is P, this is Q, so the current is going from P to Q. Whereas if I am going to switch off these two devices and then turn on the other two, I will have from Q to P. The current will go from Q to P. So I will have basically alternating voltages produced across the primary by switching action, right? Now again on this side we'll have two secondaries. Again the same center tap rectifier. So I'm going to have one diode here, and then these two, and then I'm going to have gain and inductance and resistance. So this is the load, right? So I call this as V0. Okay? So you can again write the equation for this. It should not be such a major issue. If I just call this as number of turns is N1, here N2 and N2. This is N1. So you should be able to write the equations corresponding to the on interval of S1 and S4, and again on interval of S2 and S3, and then off interval of all of the switches, right? Okay. Only thing is here each of the switches will be rated only for V in or even less than that. Think about it. If I am going to have this on, right, then I am having essentially the positive terminal connected here and negative terminal is connected here. So very clearly voltage that comes across this will be V in. It will be blocking V in when I am having any of the switches on in the same leg. The other switch will be blocking V in. So if we rate it for V in, that is good enough. Unlike what we have in the case of, push-pull and so on. Right? So that is the advantage of full bridge. You don't have to choose devices of extremely large rating. Right? The stress across the devices is limited to whatever is the voltage that it is delivering. Nothing more than that. Right? So I have not gotten into discontinuous conduction modes. Mostly I have only confine myself to continuous conduction mode. But only one converter is pending now, which is the Chuk converter, or however people pronounce it. So this converter is a very, very important converter which is having plenty of applications. So I would not like to leave it out. That's the reason we are looking at this. This also we look mainly for continuous conduction mode. That's about it. Okay. So with this, we will conclude our thing on DC-DC, discussion on DC-DC converter. So this is the last converter that we are going to discuss. This is not an isolated converter. Many of these converters also can be made isolated, because wherever inductances are there, they can incorporate a transformer. It's not that they cannot, right? Wherever inductances are there, you can think of a leakage reactance of the transformer working as an inductance. That's not a big deal. So many times what is non-isolated converter can be made into an isolated converter by making the inductance represented by a transformer. So you can make it isolated if it is required to do so, right? So let us try to take a look at this converter. This actually is generally known as a fourth order converter. Whereas many of the other converters so far, whatever we have discussed, like buck or boost or buck boost, they have only one inductance and one capacitor. So even if we write the differential equation, maximum it will be a second order differential equation. Nothing more than that, normally. So that is the reason why all those converters, the fundamental converters we discussed, buck, boost and buck boost, all of them are second order converters, whereas this will have two inductances and two capacitances, because of which we call this as a fourth order converter, right? And this is a pretty versatile converter. It is extensively used in telecom tower power supplies. It is used in some of the higher rated power supplies which may be used for different kinds of application. For example, your microwave oven, that will have definitely a power supply, right? Because it doesn't work on 230 volts. It is coming, 230 volts is coming in, but what we generate is a very high frequency wave, high frequency voltage ultimately, which is going to create the microwave ultimately, which is heating up the material that you have put inside the microwave oven. So that has an SMPS sitting inside. Many of our electronic appliances will have SMPS sitting inside, which may be requiring higher wattage capacity. So in those cases, we will normally use probably one of the converters which can withstand much higher power rating. So Chuk is one of those converters which can be used in even higher power ratings. So the Chuk converter looks somewhat like this. This is my input voltage, and I am going to have one inductance. Let me call this as L1 because there is one more coming up. Okay? And then we are going to have actually a switch, maybe a MOSFET or IGBT, one of them sitting here. So this is the switch. So the front end looks exactly like a boost converter. The boost converter starts like this, right? So front end looks exactly like a boost converter. After this, I'm going to have a capacitor, and the capacitor values chosen are generally large, because of which the ripples are generally neglected. Whatever is the ripple across the capacitance voltages, those are neglected. So this will be a capacitance. Unlike what we have seen so far in the non-isolated converters, where the inductance was mainly transferring the energy from the input side to output side, here this capacitance will play a very, very vital role in transferring the energy. So this capacitance is really going to act like an energy transfer device in this particular circuit. After this, we have a diode, and then we have another inductance which we call as L2. Okay? And then we are going to have a capacitor C2, and then we have the load here. Right? So this is the resistive load that we are considering for this. So let us try to take a look at the basic functioning of the converter. So let us say S is on. When S is on, I'm going to have this inductance storing the energy. Clearly like what happens in a boost converter. So one path is clearly it is going to just circulate a current like this. Right? So I should be able to write L1 delta IL1 equal to V in multiplied by say dt. Right? So this is as far as the inductance 1 is concerned. Let us try to take a look at what happens to inductance 2. See, this is going to get charged initially even before I turn on the switch. When I connect everything together, actually a current can flow like this because the diode will conduct anyway initially. So the capacitance would have gotten charged anyway to a value which is slightly greater than V in, because the inductance stored energy will also be dumped into the capacitor, right? Because this current will continue even after the capacitance has been charged to V in. So the inductance current will continue, because of which its energy will be dumped into the capacitor C1. So when I switch on this particular switch, because the capacitance is already pre-charged, it will be able to circulate a current somewhat like this. So it will be able to circulate a current through L2 as well as maybe the load. It will be able to do a circulation somewhat like this. So the voltage across this, if I may call this as V0, please note that it will have plus here and minus here. It will be in the reverse polarity, clearly. So this converter is somewhat similar to buck boost converter, where we had a reverse polarity at the output. So something similar to that is happening in this case. If actually I forget about this portion and look at only the output side portion, it looks as though it is a buck converter, right? Because you have an inductance, you have a capacitance, you have a load, all those things with the source as capacitance. Whatever is VC1, if I consider that as the source for my buck converter, it is essentially looking like a buck converter. Because you can look at the diode also, which is in the freewheeling direction correctly. It's not a big deal, right? So you can make out that this is essentially like a buck converter. So the front end is like a boost converter, and back end, or I can say load end, is like a buck converter. So once you turn off this switch, then this is essentially a boosting action. So V in plus whatever is L di by dt, whatever was the energy stored here, that will be dumped into the capacitor. So the capacitor gets replenished during off interval. During on interval, the capacitance is supplying actually to the load, and indirectly it is also supplying an energy to the inductor. So L2 will also be storing energy, which it is deriving from capacitor C1. So you are going to see that this current which is flowing through L2 is actually charging the inductor. So if you actually write the equation corresponding to L2, I should write again L2 delta IL2 will be equal to. Now what is the value that I have to write? This is VC1 and this is V0. So if I try to look at what is the voltage across this, this will be VC1 minus V0. Right? So I have to write this as VC1 minus V0, where I am considering the direction of current to be this. The direction of current is in this way. Right? So which is very similar to what we see normally in the buck converter. So this will be VC1 minus V0 multiplied by dt. Right? So I have simultaneously two equations being written, one for L1, the other one for L2, right? So let me write the equations here in a little bigger way. L1 delta IL1 equal to V in times dt, and L2 delta IL2 equal to Vc1 minus V0 times dt. So this is during on interval, right? Now we have to look at what happens during off interval. Right? So if I actually turn this off, the inductance is still carrying the current. The capacitance definitely has to provide a path for whatever is the stored energy here that has to be dumped. So you are going to see that when I am looking at L1, so diode starts conducting here to provide a path for the inductance, L2's current. L2 has to, continue the current. It cannot abruptly stop conducting. So you will see that L2 is essentially circulating the current like this. That's how it is going to be. And as far as L1 is concerned, this is going to be the current path for L1. So this diode essentially provides the path like a diode in the boost converter as well as the freewheeling diode in a buck converter. So it is providing a path for both. So in this particular case, I have to write V in VL1. I have to write L1 delta IL1 is going to be V in minus Vc1. Rather, this delta IL1 is decreasing. If I want, I can write this as minus. Because we know for sure that Vc1 has to be greater than V in. It cannot be less. So I can rather remove the negative sign if you want, and then I can write Vc1 minus V in. Either way is fine. Right? So this is corresponding to inductance 1's current. So inductance 1 is connected between V in and capacitor. Right? Then we'll have to write about inductor 2. So inductor 2 is only, withstanding whatever is my V0, nothing more than that. So I should be able to write L2 multiplied by delta IL2. Again, if I put a minus, I have to write minus V0. That's it. Is that minus V0? Because this is the current path. Previously, this was plus and this was minus. Now, when it is releasing the energy, this will be plus and this will be minus. Right? They are opposing each other. V0 and the inductance voltage looks as though they are opposing each other. They are in parallel, actually. They are just in parallel to each other. So, I should be able to equate now whatever is delta IL1, similarly delta IL2. Right? It should be plus V0. I have written minus here. If this is minus, is this plus? Let's see what happens, because we will have to get ultimately this is a reverse polarity. As simple as that. Okay? So let us try to take a look at here V in times dt equal to 1 minus dt. Similarly, this is also 1 minus d times t. So V in times dt equal to V in minus Vc1, rather we can say Vc1 minus V in times 1 minus d times t. So we will have this, if I take it to the other side, it will be V in itself. So I should say V0 by V in equal to 1 by 1 minus d. Not V0, Vc1, sorry. Vc1 by V in equal to 1 by 1 minus d. Exactly similar to the expression of boost. Exactly similar to the expression of boost. Right? So it looks as though my output voltage now for the boost configuration is Vc1. Then that I am connecting it to another buck, right? So let us try to look at the second one. That is when we write about L2 into delta I2, Vc1 minus V0 times dt equal to V0 into 1 minus d times t, right? Okay, so I should have this being taken to the other side. So Vc1 equal to Vc1 times d equal to V0. Of course, sign I have not taken care of. Sign has to be definitely in the opposite direction. So if I put a minus here, will it work? If I put a minus here, will it work? No, because this, if I take it to the other side, they will not get added, right? They will not get added. So let me write it in terms of magnitudes, because I know for sure that it is reversing as far as the polarity is concerned, right? So let me write it in terms of magnitude. So this is the magnitude and this is the magnitude. So I can say Vc1 times d equal to V0, right? Now using this and this, we should be able to derive the expression which will actually relate V into Vc1, right? So I can say Vc1 divided by Vin equal to V0 divided by d divided by Vin, isn't it? Which is equal to 1 by 1 minus d. I am just writing here and writing from here, both. So I should be able to say V0 by Vin equal to d by 1 minus d. Right? Vc1 by Vin equal to 1 by 1 minus d. That's what I have written. 1 by 1 minus d. And Vc1 we have written as V0 divided by d. So I have written V0 by d. So V0 by Vin is d by 1 minus d, which is similar to your buck-boost converter. Right? So we will have V0 by Vin equal to d by 1 minus d. Of course, if I put a negative sign, I have to only remember that it indicates the polarity is in the opposite sense. That's it. Nothing more than that. The polarity is exactly in the opposite sense. So it is very similar to buck-boost, but it is basically a versatile converter more than any of the basic non-isolated converters, because I have several variations that I can do, and also the energy transfer mainly takes place because of the capacitance, and inductances generally are more difficult to design even at higher frequency as well as lower frequencies. Inductances are even more bulky as compared to capacitances. But generally, that's why in most of the integrated circuits, they would like to avoid inductance completely if it is possible. If you can somehow simulate an inductance by using something else, then that will be great. But otherwise, generally they tend to avoid the inductances as much as possible. Because here energy transfer takes place with the help of a capacitance, this is considered to be much more versatile as compared to rest of the basic non-isolated converters, right? So much so for our DC to DC converters. So we had seen mainly the basic three converters, buck, boost and buck boost, and then we looked at Chook converter just now, and then we had looked at non-isolated converters, which are basically 5 converters we had seen: flyback, forward, push-pull, half-bridge and full-bridge. So DC-DC converter is really not a very vast portion as much as rectifiers, what we saw, but the next portion what we are going to venture into, that is definitely a vaster, much vaster portion. Not probably again as big as rectifier. So inverters, very clearly this is going to convert DC to AC. And one of the most versatile circuits which are used everywhere, literally. So this invention of inverter has really propelled the induction motors to be used in all sorts of applications. Wherever we had variable speed, requirement. Induction motors earlier were not being used so much. Synchronous motors, there was no scope to use it in variable speed application because we had only 50 hertz and it could run only at a particular speed, nothing more than that. So when we want actually variable speed to be achieved, frequency necessarily needs to be changed. 120 F by P, which is synchronous speed. So very clearly, inverter, once that has come into picture, we have had, versatile applications for synchronous motor as well as induction motors. And synchronous motors normally have a better efficiency than induction motor, because of which the variable frequency inverters have really made synchronous motor to be applied in several applications where it was a no-no earlier. At least induction motor has a small variation in the speed. Synchronous motor does not even have that when you have a constant frequency. So now synchronous motors are being used in many other applications where variable speed drives are important, right? So the basic principle of inverter operation is whatever we had seen in full bridge. For example, if I have one switch, second switch, third switch and fourth switch, which I call as full bridge inverter, right? And what I have is a voltage source. So we call these things as voltage source inverters. There are two types of major inverters that we see. One is voltage source inverter and the other one is known as current source inverter, which means the voltage source has to be necessarily converted into a current source by including a large inductance in series. If I put a large inductance in series, the inductance will not allow change in current so easily. So it will look as though I have converted the voltage source into a current source, because naturally there is no current source concept, really it is available. Everything is a voltage source generally. Whatever we have is a voltage source. So if I want to make it as a current source, I necessarily need to connect a very large inductance in series. So VSI and CSI, current source inverter, which is generally specified as CSI. So this will require a large inductance on the DC side. Similarly, I may require as a dual large capacitor on the DC side as far as the voltage source inverter is concerned. If I have, for example, a diode rectifier, I will have oscillating voltage. I don't want to have an oscillating voltage. I want to have a steady voltage. So if I want a steady voltage, I have to put a big capacitor in parallel. So here, a large inductance in series on the DC side, whereas here, a large capacitance in parallel on the DC side. So two are dual of each other, basically, right? So if I am having a circuit like this, which is S1, let us say this is S4, this is S2, this is S3, and I connect the load here. In full bridge DC-DC converter, we had connected the primary of the transformer winding there. That's all is the difference. Whereas here I am directly connecting the load, which will require the AC supply. Maybe a single phase induction motor, for example, right? So when S1 and S4 conduct, I am going to have essentially a current this way. Whereas when I am going to have S3 and S2 conduct, I am going to have a current in the opposite direction, right? So by alternately turning on S1, S4 and S2, S3, I should be able to get alternating voltage across the load, which is definitely not sinusoidal. Agreed. It is going to be non-sinusoidal, no doubt, right? So this is one of the voltage source inverter circuits which is very, very fundamental in terms of its functionality. I can probably control the turning on and turning off of these switches ultimately to arrive at maybe sinusoidal voltage if I have some kind of special control technique, which we'll have to look at eventually, right? But if I assume that I'm going to turn on S1 and S4 for 50% of the duration, and I'm going to turn on S2 and S3 for 50% of the duration. So this is T by 2, this is also T by 2. Of course, I will have a small dead band. Forget about that. That will maybe only a few microseconds or something. So out of 20 millisecond cycle, few microseconds I can neglect. That's okay. Right? Dead band I will require between these two. I can't really have this on immediately. Maybe I'll have to delay it slightly. Right? This will give me actually, this voltage will be, if I say VDC, this will be plus VDC and this will be minus VDC. Right? So, if I look at the RMS value, it will correspond to VDC itself. The RMS value will be VDC. So, I have mainly couple of disadvantages when I am going to make this like a square wave inverter. This is known as square wave inverter. I am essentially having T by 2 and T by 2, positive half and negative half. I cannot control the RMS value of voltage. This is one of the major problems that I am going to have. If I have a fixed value of DC, I will also have a fixed value of output voltage. Right? The second thing is, because it is square wave, it is far from being sinusoidal, it will have so many harmonics. Right? So all these harmonics are going to create a problem, especially if I am going to apply it to a motor. Because motors require sinusoidal voltages and sinusoidal currents. So I am going to have the trouble of not being able to eliminate the harmonics and not being able to control the RMS value. That is why we have several control techniques called pulse width modulation, which is PWM. So we will use a lot of pulse width modulation control. What I mean is, rather than having a pulse for complete 180 degrees, if I have a pulse only corresponding to this much. Similarly, maybe I have a pulse only corresponding to this much. For quite some time it is zero voltage. I'm going to have a pulse only starting from, let us say, 45 degree and it will go until 135 degree, for example. Right?